Hi, welcome to Lesson 12A, Vectors and Scalars. The goal of today's lesson is to understand the difference between vectors and scalars and how they interact in our daily lives. So, we may have heard of the word a vector before, or scalars, for example. When we speak of those things, a scalar is a quantity that only has magnitude. There's only some sort of size to it. So a scalar may have, or may be something like the mass of some object. It could be a temperature. It could be a dollar amount or some sort of monetary value. It could be some distance where we don't know the direction. Could be speed. Speed is obviously how fast something is going. It's measured in distance divided by time. That's how you calculate the speed. But speed is different from velocity, where speed, the direction is not noted. So those are all scalars. A vector, on the other hand, is a quantity that has both magnitude and direction. Okay, so a scalar just has magnitude or size, and a vector has magnitude and a given direction. So like I mentioned before, velocity is one of those, because we know in velocity we have a speed and a direction is given. I mentioned up here mass being a scalar. Well, weight is a vector because it's the mass under the influence of gravity, and gravity has a direction pointed down towards the center of the earth. There could be other vectors like for example, the direction of the wind blowing, for example. We could state that the distance that somebody has traveled in a specific direction. Okay, so those are all vectors. We can represent vectors by drawing arrows, and these arrows have a length, which is the magnitude, and it has a specific direction, and the direction would be the gradient of the line, or this ray, drawn on the piece of paper that we've drawn it on. Vectors have a beginning or initial point, also called the tail of the vector. So where the vector originates, that's the tail of the vector, and it ends. The terminal point of the vector is also called the head of the vector, and that's where we draw the arrowhead. So vectors have a magnitude and direction, meaning length and gradient, or it could also be some sort of a cardinal direction in terms of bearing, or in terms of a certain number of degrees north or south or east and west kind of thing, or combinations of those. So we'll be looking at those in a little bit. So vectors, of course, have magnitude and direction. Scalar has no direction, it just has the magnitude. So it would just be a number. We couldn't represent it with a ray in this case. Now, there are things called position vectors, and position vectors give the position of a specific, either a position vector or a specific point on a Cartesian plane with respect to the origin. So a position vector would originate at the origin and then terminate at some sort of point. So suppose we have a small Cartesian plane here, and we have the x and the y, and so a position vector will originate at the origin and point to a specific point. So if we're talking about this point right here, that would be 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, so -3. So 7, -3 is this point. The position vector of that point is vector 7, -3. Is written in sort of in kind of combination form, where we would write this out when we were calculating probabilities in the past. We were looking at 7 choose. We can't choose -3, but it's in that kind of form. So the vector is written in this as a column vector like this, 7, -3, which means that the vector is from the origin 7 units to the right, or 7 units horizontally. In this case it's right because that's positive, and then 3 units vertically down, 3 units down from the x-axis. And so that is how we draw, or how we would represent this vector. And the position vector originates at the origin and terminates at the point that we're discussing. Okay, so the origin is O. Suppose this point is point A. This vector could be written as OA. Actually, no, this vector can be written as vector OA, or if we just name this as vector A, it can be written like that, or just a bold. It could be just a bold A that you might see in textbooks, or it could actually be even besides just with the vector symbol on top, with a little tilde on top. So these are the different ways of writing the vector. The length of it, if we were to just put absolute values, well, it's not absolute value, but that's the magnitude of vector OA, the magnitude of vector A, like this. So we just put the magnitudes on it to find the length of that. And because it's not perfectly horizontal or perfectly vertical, it's on some sort of a diagonal, we see that we've gone 7 units to the right and 3 units down. It's negative because it's downwards. I was going to say south. If we're using cardinal directions, it would be south, but this is like 3 units down from the x-axis. And then the magnitude, well, because that's a right triangle, we would just use Pythagorean theorem. So magnitude OA would be 7 squared plus -3 squared, and the square root of that, which would then give us the square root of 58 units. So that would be the magnitude of this vector. Vectors can also be written, if I were to draw some other vector like this, and I'm saying this is vector AB. Well, a vector AB, it's written in order from the tail to the head. So this is point A, and this is point B. And if the vector goes from point A to point B, it's written like this, vector AB. So this is the position vector of B relative to A. Okay, so it starts at A, ends at B. The position of B relative to A. Now, there can be many different types of vectors, or not many different types, I guess many different positions and directions of vectors. So we could have a vector U, like that, for example. We can have vector V, like this. We can have, I'll draw this like this here, vector CD, and erase this one briefly. So we can have a bunch of different types of vectors. In order for vectors to be equal, they have to have exactly the same magnitude. I hope I drew those exactly the same length, and exactly the same direction. So these vectors, A, B, and C, D, are heading in the same direction. They have the same gradient. Okay, so they've got the same y step and the same x step, or the same change in y over the change in x as each other. So they have the same gradient. As cardinal directions, they would have the same east and west, or the same degree of separation from the north or south or east or west axes. So they have the same gradient and the same magnitude. So those are equal vectors. Vectors u and v here, they are parallel, but they're not in the same direction. They do have the same magnitude as I drew those, well, it's roughly anyways. These are supposed to be having the same magnitude, but they're in opposite directions. So in order for them to be equal, they have to be pointing, the head of the vector has to be in exactly the same direction, and they have to have exactly the same gradient, meaning they have to be parallel. If they're parallel but heading in opposite directions like this, that means that these are called opposite vectors. And where I would draw up here, or write that vector AB is equal to vector CD, here I'd have to say that vector U is equal to negative vector V. And the negative, if I say they're equal now because of this negative, that negative actually would turn this vector V around. So if I wanted to say that vector U and vector V are equal, well, I couldn't say they're equal because they're in opposite directions, but that negative vector V would then be drawn like this. So this is now negative vector V here. So U, vector U, equals negative vector V. Or we could state that vector U is equal to the negative of this vector V, meaning of course that it would turn around to give that. Okay, so these are opposite vectors because they're parallel, but they're pointing in opposite directions. If I used something like this sort of notation where I have point-to-point vectors, if I had this vector here and I'm stating that they are parallel and opposites, let's say this is vector FG, I could say vector AB equals negative vector FG. And so that negative could turn the vector around, therefore vector AB is equal to vector GF. Okay, because negative FG is going to be the same as vector GF. So vector FG and vector GF are not the same, but negative of vector FG is equal to vector GF.